In this video, I give a brief introduction to my research. The interaction between electrons leads to equations which are too complex to be solved exactly. Therefore, approximate, computationally cheap methods must be developed. Within quantum theory, a system's observable properties are calculated from the wave function. While the laws of physics which govern the electron's behavior are known, the exact computation of the wave function is impossible in most cases. Therefore, alternative formulations of quantum mechanics must be considered. Density functional theory states that anything that can be calculated from the wave function can instead be calculated from the electron's probability density, the chance of finding any electron at a given point in space and time. The electron density is a much smaller object than the wave function because it only depends on one point in space regardless of the number of electrons in the system. However, it's generally unknown how to extract observables from the density. Additionally, one must calculate the density without the wave function. Kohn and Sham proposed that the electron density of the interacting electrons can be calculated from an auxiliary system of non-interacting electrons. The lack of interaction in this fictitious Kohn-Sham system means that the equations which describe the electron's behavior can be solved for many electrons. The non-interacting electrons feel the Kohn-Sham potential, which ensures that their density exactly equals the density of the interacting electrons. However, the exact form of the Kohn-Sham potential is generally unknown, and therefore must be approximated. The exact Kohn-Sham potential can be calculated for small systems. Examining this potential is extremely important when developing advanced approximations. Studying theories within quantum mechanics in the absence of approximation is the backbone of my research. It allows me to determine why cutting-edge methods, such as density functional theory, fail in important scenarios. The idea code enables me to study small systems for which the exact wave function of interacting electrons can be calculated, which in turn gives me access to the exact electron density. First, we define a system by choosing the external potential, and then the number of electrons. As we need to calculate the exact interacting wave function, we are limited to up to 4 electrons in one dimension. From the exact density, we reverse engineer the Kohn-Sham equations and find the exact Kohn-Sham potential. We can then compare the exact potential against commonly used approximations. This method of investigation has thus far been successful at determining fundamental properties of Kohn-Sham density functional theory. The idea code can be used to calculate any observable, not just the density, and hence the code can also be used to investigate other approximate methods within quantum theory, such as many-body perturbation theory and hybrid density functionals. Further details can be found below. My research interest can be split into 3 categories: electron dynamics, which deals with the motion of electrons triggered by a perturbation to the system, e.g. an electric field; electron excitations, in which electrons jump from one energy state to another, for example, owing to a laser pulse; and electron emission, measuring the energy and probability that an electron is absorbed or emitted by a material. Below, I give details on my research in these fields.